Now, there are a couple of different models of population growth that I want to show you, which are the most commonly used ones. One of them is called the exponential growth model. And if you're following spread of COVID-19, that's the model that you've been seeing all over the news. It's like a curve that looks like this. Just understand this curve here. This is population size on the y-axis and generation on the x-axis. And you see that this curve has like what we call a J shape, like starts slow and then increases faster and faster. With the COVID-19, what you're seeing is here on that y-axis will be spread, so number of cases, right? So number of humans who have the virus. And on the x-axis is actually days, right? So it's in days. I mean, this spread is being so fast. But let's understand kind of how this curve here was built, this specific one. So if you look at the top part of this diagram, each of these red dots would represent an individual. So let's say this is a bacterium. And bacteria, if you guys remember, reproduces asexually by binary fission, meaning that every time a bacterium divides, it's going to divide into two identical bacteria. And each time that these offspring will divide, they're going to make two others. And then their offspring will make two others, and their offspring will make two others, and so forth. So bacteria is kind of like a great example of exponential growth, because whenever one reproduces, it produces two offspring. How you define exponential growth is this: the rate of increase is constant. And in this case, the rate of increase is this, is doubling. Each generation is kind of doubling because it's going from 1 to 2, from 2 to 4, and so forth. Because it's constant, what happens is this, is that if you would plot these individuals now into this curve, this is what you get, right? So you start with 1, and then you have 2 and 4 and so forth, right? And then it starts increasing. But notice how the curve shows their increase. You have in the beginning, because you have very few individuals, even though they are doubling every generation, so it's still the same kind of rate of increase throughout the curve, because there are few individuals in that population to start with, the growth is slow. So the slope of this curve is mild. But as the number of individuals accumulate, now that doubling means a lot, right? So when you have 1, you're doubling to 2, or 2 to 4, that's not much. But when you have like 24 and then suddenly you have 48, or 1,000 and then suddenly 2,000, you see that the number of individuals increases exponentially. Even though the rate of increase may be the same, the number of individuals is increasing exponentially. So what happens is it goes from this kind of mild slope to the slope increasing, becoming steeper and steeper and steeper and steeper. So when you have a high number of individuals, that population is just booming. Okay, so there's a huge amount each generation or each month or each year, whatever, however you're measuring this. Here's another example of a more unlike type of animal that has shown to grow exponentially under certain circumstances. Elephants would not normally grow in an exponential rate. They're very long lived, the pregnancy time is very long, so it's usually not what would you expect. It's nothing like a bacterium. This is a population of elephants from Kruger National Park in South Africa. What happened was that the population of elephants was very low. They were being poached quite a bit earlier in the 1900s, and the population of elephants was very low in the park. So they decided to really protect the elephants, and they set out to put lots of guards in there. They prohibited poaching, and they were really successful in their restrictions, and pretty much the elephants stopped dying in the park. And what happened was that they just shot up. So they increased so fast in population that later they had to open for hunting in order to control and manage the population growth of elephants, which is something like you wouldn't expect, but it can happen. Okay, most of the time this is not what would happen to a natural population. It may happen in situations like this. So this species was completely protected, nothing was killing it, right? It's long-lived, so the number of individuals accumulated fast. But you can see this would happen very commonly, like in the situation of an invasive species. So an invasive species is a species that hasn't naturally evolved in an area. So it has existed in that area for less than 500 years, which would indicate that that species has been brought to that area either directly or indirectly by humans or human activity. And once this non-native species arrive in a new area, if they find the resources that are adequate for their growth, like climate is good and they have everything they need to grow, what happens is that they start to grow pretty fast. Different from native species is that they don't have predators in there to keep them in check. And because they don't have predators to keep them in check, they just grow exponentially. So you find this in these kind of less natural situations, right? So when the elephants are being protected from being killed by anything, when invasive species are just arrive in an area and have no predators to keep them in check, or bacterium growing in a dish, right? So you have these not so natural situations that you will find exponential growth. Or a virus that just like mutated recently and it's now spreading through the population, right? Spreading really, really fast. So this kind of also like not a common situation, natural situation. More realistically, you would have populations growing in what we call a logistic type of growth, which is this one that's shown in this graph. And you see what happens in this one is that the population will grow exponentially. If you see like the beginning of this graph here is exponential. So that population will grow exponentially, but in a natural setting, what's going to happen is that eventually, if there are too many individuals of that population, the resources are going to start becoming limited. And there would be a lot of competition between them. So the growth rate is going to start declining after a while. So here, if you look, the curve is mild in the beginning, just like exponential growth, and then gets steeper, steeper. But then instead of getting steeper, steeper, and steeper, it stops getting steep and it starts becoming more mild again. Mild, mild, mild. And even like very, very, very low growth, you see like it changes the direction of the curve to the point that that curve kind of flattens out. And when it flattens here, what happened is that the population has stabilized. Now, who can tell me what a stable population would look like? What's happening to this population?
It's reaching its carrying capacity.
Okay, yeah, it is reaching the carrying capacity, but okay, but what's happening to those individuals? So let's say this. Let's say in this case right here, so this is a paramecium example, and paramecium, remember, is a protozoan. So imagine I'm growing this in a dish in the lab, and I have a dish in a medium that has all the nutrients necessary for that paramecium to exist. Okay, all the food it needs, everything, space. So it has plenty of space, plenty of food. It's going to start growing really fast, really, really fast. But we get to a point that suddenly there's so many in there that they're going to start competing for food, competing for space, and the growth rate is going to start slowing down and stopping in a sense, right? So stop growing. But what's happening there? Did they completely stop? Like, like
They level
what's
off because
happening?
there's no emigrating or immigrating, so there's nowhere to go. So
There's
it's like
nowhere to go. Good. So what's happening to the other two factors then? What did I say? A population is stable when what?
The birth rate and the death rate are kind of equal.
Correct. When birth rate equals death rate. Okay, in this case, because in a dish, there is no immigration or immigration. Okay, so there's no new individuals coming in or individuals leaving, but the number of births equals number of deaths. So I want you to understand that when the curve flattens here, it doesn't mean that they stopped having babies and stopped dying, so it's all the same individuals. No, the individuals are changing, but the same number that is being born is actually dying. Okay, so that's what this flat part of the curve indicates. This point here, where it flattens, is what we call the carrying capacity of that environment. And carrying capacity, what that means is the maximum population size. So you're talking about a specific population that environment can sustain. Okay, so in this case here of my dish with paramecium, the carrying capacity of my dish, so notice that it's not the carrying capacity of paramecium, it's the carrying capacity of the environment. So the carrying capacity of my dish for paramecium is maybe 900 paramecium. It's given in number of individuals of a specific population, but it's a characteristic of the environment in relation to that population. So we characterize this not by a J-shaped curve like the previous one, which was the exponential growth, but this one we call it an S-shaped curve. And if you look at this red line, it looks more like an S shape. One thing I want you to understand is that rarely, okay, a population is going to just, oh, okay, so now the exact same amount of births is the exact same amount of deaths. This is, of course, unlikely to happen. A more likely situation will be something like this. This is just another organism. This is a water flea, Daphnia, and you see, like, it went up. It went up to a point, and then went way over the carrying capacity, and then it kind of collapses because it went way over the carrying capacity and went down. So it's kind of going to oscillate a little bit along this line.